in space. Light has no charge. It has energy. It's according to its intensity and frequency and wavelength, but it has no electrical charge, and so he's saying that the wave propagation is same. Light through a vacuum and electricity through the electric field. Its interaction. To be sure, Maxwell still tried to interpret his field theory mechanically by means of mechanical ether models, but these attempts receded gradually to the background following the representation purged of any unnecessary additions by Heinrich Hertz, so that in this theory, the field finally took the fundamental position which had been occupied in Newton's mechanics by the material points. At first, however, this applies only for electromagnetic fields in empty space. In its initial stage, the theory was yet quite unsatisfactory for the interior of matter because there two electric vectors had to be introduced, which were connected by relations dependent on the nature of the medium, these relations being inaccessible to any theoretical analysis. They're empirical, yet they're attached to the diagram, so they don't reflect the points so much as the connections and the boundaries. So they are incongruous to the fungible part, which results tractability of the analysis, or the deconstructive account to the fundamental elements and the layers talked about the analysis. The theoretical analysis is this sensible, fungible, and tractable. An analogous situation arose in connection with the magnetic field as well as in the relation between electric current density and the field. So these days we talk about its electron holes, and there's passive and active electrical circuits, or Ohm's law and Kirchhoff's law, and that voltage is electromotive force is defined by what kinetic action results from its dissipation in a circuit, what it can drive. Amperage results from Ohm's law. According to Kirchhoff's law, there can be active circuits and current devices whose resistance breaks down given current, devices whose resistance increases given current. The dielectric materials, which are insulators but have a particular gap that at some point will begin to induce capacitance, and into all the quantities of current with respect to those being standing fields, that as well they represent the motion of electron holes that each at some point in time makes for there's basically two electronic digital devices. There's edge detection and level detection. So there's rising edge or falling edge, and then there's when the voltage drops or increases, that can be detected, or when it reaches a particular level, the current or that. So these kind of rising falling edge bits or edge and level detection are these triggers. Those are the gateways in the what's called the PNP or NPN semiconductors, which implement transistors on the chip or digital logic. Because then it's not like how many electrons is it? Well, it's modeled that way, but mechanically it's only implemented as about this capacitance and currents. Best I heard. I worked in fabless semiconductors, so in a room full of electrical engineers, I was a software verification guy who had the fundamentals and background. So anyways, so that in this theory, the field finally took the fundamental position which had been occupied in Newton's mechanics by the material points. At first, however, this applies only for electromagnetic fields in empty space. ... Initial stage, theory was yet quite unsatisfactory, as in now the situation arose connection with the magnetic field, as well in the relation between electric current density and the field. And now Einstein introduces the preliminary to his milieu. Here, H.A. Lawrence, Herbert, or Hendrik, I guess it was, Hendrik Anton or whatever, Lorentz found an escape which showed at the same time the way to an electrodynamic theory of bodies in motion, a theory which was more or less free of arbitrary assumption. His theory was built on the following fundamental hypothesis. Everywhere, including the interior of ponderable bodies, the seat of the field is the empty space. The participation of matter in electromagnetic phenomena has its origin only in the fact that the elementary particles of matter carry unalterable electric charges, and on this account are subject on the one hand to the actions of ponderomotive forces, and on the other hand possess the property of generating a field. Elementary particles obey Newton's laws of motion for the material point. Now this, he says, is Lorentz's theory. The following fundamental hypothesis. And that's a pretty great thing, because what it does is it relates that the ponderomotive forces are what could possibly be causal and indicate the electromotive force of the motive, and that the particles are basically classical particles. So everything that whatever results as a field must have a classical definition somehow, even if it's moving backwards or lack thereof, or somehow, however it's so dissipative and restitutive, and that it's attenuating or cyclical, this must be the way. So then he has that it's the charge is the quantity. So just like there's been discussion here, it's like, well, yeah, mass energy equivalency and charge energy equivalency, but matters mass, and electricity's charge are quantities, and they're two separate things. And so when that builds a strong nuclear force, and for the electric force, those are complementary duals, this thing. And it's not so necessarily so that one or the other of those has to be first, but the kinetics is first, because it also works up the thermodynamic, and also the transmutation elements kind of comes out after, when you combine the weak and electroweak back together again, because mesons and hadrons, and some of them are charged, and why is that a lepton, and this kind of thing. Cross families this way. So I mean that's where the fundamental theory is usually just like, this is mechanics or kinetics and kinematics, and this is electricity and magnetism and ... And let's not talk about the radionuclear at all, because it's just too dynamic, or we're gonna leave that out, and it's already, there's nothing we can't really manufacture it in the usual setting like we can these other devices. But it's just as, otherwise you could frame it as the center of the theory. It's just that the epochs are different. So anyways, the elementary particles obey Newton's law of motion for the material point, which is a continuum mechanics. This is the basis on which H.A. Lorentz obtained his synthesis of Newton's mechanics and Maxwell's field theory, that the light waves are ohms, and then the electrical field is basically free in space, unless it's boxed by a Faraday cage or something. The weakness of this theory lies in the fact that it tried to determine the phenomena by a combination of partial differential equations, Maxwell's field equations for empty space, and total differential equations, equations of motions of points, which procedure was obviously unnatural. I'll need to study that. The unsatisfactory part of the theory showed up externally by the necessity of assuming finite dimensions for the particles in order to prevent the electromagnetic field existing at their surfaces from becoming infinitely great. Here that might be necessary in a sense, that to define things, figure out how to define things in terms of the infinitesimals inside, that is kind of the opposite of electron physics. It's electro weak physics, or this kind of thing. Maybe, and so there already is an electro weak physics, and I'm not meaning to imply that there's such a relation already in terms of that, but if it's infinite at the surface, you call that one, and define the inside as infinitesimals, and that's how you make an analysis of it. The individua of a continuum. The theory failed, moreover, to give any explanation concerning the tremendous forces which hold the electric charges on the individual particles. This is kind of like this infinite tension model that also breaks opposite everywhere or something like that. That it makes it possible to have this kind of first you need a model for that mentally and mathematically and free of resolution of the paradoxes just by its plain consideration as a thing, and then you can attach it to the physical model and call it automatic equipage of the model with an interpretation. So otherwise that's necessary for something like this kind of theory. And also, it might have been the wrong time to apply it to something like that, because then if you would have figured out, I know what a total field theory has to be, so I'm going to apply it to just where I ran out of the classical field theory. I was like, no, you just painted a smaller box, and so that'll work, but you still need to let that back out. It wouldn't be true, and so you'd end up having to work that numerical methods either way. This could still be done, but it's just with these kinds of things in the middle, in the milieu, in the mesoscale for our micro and macro, that we all live in the meso, the classical. That's the way it is. Reasoning, the ponderable. The theory failed, moreover, to give any explanation concerning the tremendous forces which hold the electric charges on the individual particles. H.A. Lorentz accepted these weaknesses of his theory, which were well known to him, in order to explain the phenomena correctly, at least as regards to their general lines. Thus, we might imagine that Lorentz maybe had a second book, and he's like, by the way, here's a bunch of empirical stuff I figured out. And so a lot of the people who got like their classical things are also like, by the way, here's a lot of this. Here we're looking for Einstein's secret notebook, where it has all this other stuff, which he would never want to subject to general critical review, because people would attack its non-mathematicality or non-scientificality or something like that. Not that those are words, but anyways, that's on hypothesis and conjecture, obviously. It doesn't exist in a multiple worlds hypothesis. Furthermore, there was one consideration which reached beyond the frame of Lorentz's theory. In the environment of an electrically charged body, there is a magnetic field which furnishes an apparent contribution to its inertia. This is like space contraction in the sense that the standing field can make for it is so that and then this inertia is kinetic quantity, so that mention of the Meissner and Meissnerized ingot, whatever, that's the idea in the that these are effects that, according to various other magnetic effects, that it reduces what would otherwise the slippage and makes it so that it's possible for it to an object like a Gauss gun's projectile to slip through and to have more inertia for one of his inertial systems, Einstein's, as to why it's directional instead of non-directional. Kind of like there's a notion of a discussion before of the electric three-phase motor that has according to three phases of alternating current at each one, where it rectifies or gets regulated or transformed. And then it applies a really constant electromotive force applied to a motive force given a very constant load. And so it starts in an astable configuration, and then you have to get it started one way or the other. It'll just sit there. But then when it does, it makes for a constant draw. So it's just similar when he's describing some of these magnetic effects, that it's possible to make something that's magnetized as its own magnetic field permanently, because it's baked in, it's built into its structure, as when it achieved a phase reaction from a very hot temperature where it was molten to when it was put in a magnetic alignment, then it was reduced to a solid when it maintained that magnetic alignment, or the magnetic monopoles, that then it results that it lives in a field where that field basically has directionality with respect to it. So this is, I think, what Einstein is describing about this inertia that doesn't match the classical laws of kinetics, because his magnetic field doesn't match the superclassical laws of the magnetic field. Should it not be possible to explain the total inertia of the particles electromagnetically? It is clear that this problem could be worked out satisfactorily only if the particles could be interpreted as regular solutions of the electromagnetic partial differential equations. It is clear that it was very clear that that's a direct inference. There is a paucity of terms, and because there's not a deconstructive account explaining that the superclassical effect holds, that there is only the classical effect. You need to build that into it. So yeah, it is clear that, given what's given, it is clear. But he doesn't say it is proven that. It is my total opinion that I'll maintain forever that it will never not be the case that. He doesn't say that. He just says it is clear that this problem can be worked out satisfactorily, and satisfactorily means successfully. And from his earlier definition, only if the particles could be interpreted as regular solutions of the electromagnetic partial differential equations, which is everything that was able to define things by time and continuous time and as a stable system. The Maxwell equations in their original form do not, however, allow such a degree of description of particles because their corresponding solutions contain a singularity. Here then, that's kind of not so much because E cross B is a classical field and it's got gimbal lock or what. That's kind of, today we talk about the nonlinear terms and stuff, so I think what he's saying is that the field back then, when they hit this place where they couldn't really go beyond that, they said, well, you don't want to try because there's a singular solution, and so there exists none. Now, go back and learn the rest you need to know to build these motors, and leave this sort of theoretical maunderings to the graybeards who've got the right attitudes. And that's, not exactly how it is, because anybody is supposed to, when they see something like that, and they have an explanation otherwise, it's almost upon them, like per one of Einstein quotes I heard one time, that they have to take a chance at it. But it's also here, it's like, at least there's a reason why, if you're going to fix that, you got to fix this too. But a singular solution is not necessarily the same thing as there not existing these superclassical solutions. So, just to be said that is not consequent. That it still might be a system of solutions that emits a singularity, but it might have also emit superclassical solutions that fix it. Theoretical physicists have tried for a long time, therefore, to reach the goal by a modification of Maxwell's equations. These attempts have, however, not been crowned with success. Thus, it happened that the goal of erecting a pure electromagnetic field theory of matter remained unattained for the time being, although in principle, no objection could be raised against the possibility of reaching such a goal. The thing which deterred one in any further attempt in this direction was the lack of any systematic method leading to the solution. What appears certain to me, however, is that in the foundations of any consistent field theory, there shall not be, in addition to the concept of any field, any concept concerning particles. The whole theory must be based solely on partial differential equations and their singularity-free solutions. I don't know that that's so, because whatever is tractable essentially as a body will eventually be a particle in a sense. And so now, but it's for, if maybe to say in the foundation of any consistent field theory, so let's see, Maxwell's field theory, optical and electrical phenomena. So only in the realm of special relativity? No, because there's still the points will define what's the quasi-invariant with respect to measuring the continuous, because the individual of a continuum in geometry is a point, and then that's built to partial differential equations and their singularity-free solutions, I guess that's fair, because then these things as continuum mechanics will still have solutions of that, and then you could say that his theory is framed in those. But those elementarily and fundamentally are according to their deconstructive accounts. So he is saying, though, that it's not usual matters of linear analysis. And then besides, these days, besides the partial differential analysis, we have this nonlinear partial differential analysis. So these might reflect, and these were discovered and publicized that since this was written. So I'm going to generously read that as just that it must be continuum mechanics, because it's about the material points. There are none. These are waves. It must be continuum mechanics. Now, the next section says the theory of relativity. Talks about principle of the inertia of Galileo, fundamental hypothesis of the theory of relativity, which theory has led to an unexpected expansion and broadening of the field theory to the superseding of the foundations of classical mechanics. Assesses the Maxwell-Lorentz theory, the Laplacian, the Lorentz transformation, and the Laplacian being basically the same bit. Back to the Lorentz transform. Now I want to look at the Lorentz principle again. Everywhere, including the interior of ponderable bodies. Here, that's their space and stuff like that. Einstein's talking about his arguments about the electromagnetic field here, and how light also has to behave kind of the same way as waves. Vis-a-vis, otherwise all his mechanics is points and parts, and then his field is like, the field is for waves, the space is for points. Einstein's left these kind of next to each other in the space-time field here, about whether or not it's a vector field and it's continuous manifold. He doesn't say it's not a continuous manifold, and he doesn't say that He doesn't say that it's ridiculous to have the electric fields are defined in terms of particles, because electron volt is an arbitrary quantity that's really vanishing. For something like that would really say, and so it's like, it must be defined in terms of these continuous terms. But again, we can really attain to making that a continuum mechanics also, with points and atomism and having complementary duals. That here again for reading for Lorentz. So the Lorentz transforms is about the Laplacian and setting up the Laplacian, and that makes for PDEs. That it makes for setting up the Hamiltonians. It makes for setting up the gradient. It makes for setting up Green and Stokes, Navier-Stokes, and all the linear methods so follow, which are so relevant in predicting these things, which are relevant when you're trying to compute an ephemeris or these kinds of things, or trying to compute these matters of conversion and ... or the special relativistic effects with regards to propagation, this and that, and ... But this Lorentz's principle is not necessarily just so about the Lorentz transform, because we can think about something else besides the Cartesian basis, like a principal component analysis basis that will provide instead of, for like, I'll give you a Lorentz transform on a Cartesian space, and then I'll ask you to do a principal component analysis on the same space. And now you'll notice that though they have the same origin, though after the principal component analysis, the origin, it has a different orientation. And what's nonlinear in the one is linear in the other, for the cases with the highly nonlinear things that add up about singularities and the singular surfaces and this kind of stuff. So this makes for the free analysis in the field when he says, for example, that, it must be solved by PDEs with no singularities. And then it's also like, well, if you can do that via a free analysis and an original analysis, then I got no problem with that. He might be like, whoa! He would approve. As long as it can be explained fully to his model of a physicist and given entirely in self-contained form in a free of arbitrary pondering formalism to his model physicist. Everywhere, including the interior of ponderable bodies, so this is Lorentz, and then for Einstein it's like, and so this includes their space and my space that I have of them. The seat of the field is the empty space, and so the seat of the field here would be the origin, and flat empty space. The participation of matter in electromagnetic phenomena has its origin only in the fact that the elementary particles of matter carry unalterable electric charges, and on this account are subject on the one hand to the actions of ponderable motor forces, and the other hand possess the property of generating a field. The elementary particles obey Newton's laws of motion for the material point. And so this is before quantum physics, and so generally, well, it's so that in quantum electrodynamics, charge is a conserved quantity, and that current is the force carrier, and electrons are the force carrier for these particles, or electron holes, rather, is the usual way of talking about it today. Otherwise, this is classical. It's a classical notion of an electric field's interaction with a magnetic field's interaction with a field occupation numbers of massive bodies that have any particular interfaces which reflect magnetic interference, that the passage of the magnetic field makes interference which causes things to move, just like the armature of a winding of a motor coil makes exactly how electric motors move, which I've forgotten but once knew, or anything to do with like how electromotive works for the linear accelerator. So here's how you can make a hopper and make a bunch of wire wrappings and some silicon controlled rectifiers, say, and some coils, and then pour a continuous stream of BBs into the hopper and have them shoot across the room at a drawing wall current, or the coil gun. So linear motor, or like here's how you can magnetically levitate a train, thus that its friction with its tracks is zero, and then propel the train as of the train with grand vitesse. Maglev. These are the kinds of things that get into, the applications of magnetics, besides stuff like, well, let's just talk about the radio frequency, and what we want to really get figured out is how to have, using the least amount of bandwidth possible, to fit the most high frequency data through it, and just try to keep it so that not everybody gets brain cancer. These are the kinds of things that people have to figure out. But Lorentz has basically got it that he's got a classical way, at least, to say two things. On the one hand, to the actions of ponderable motor forces, and on the other hand, possess the property of generating a field that's non-local. So then his particles, he says the elementary particles obey Newton's law of motion for the material point, and that's basically particles go straight. Particles, they have a velocity and they go straight. That's particle physics. And then they live in these fields, and then they have forces that apply to them according to scattering and tunneling theory. And the quantum properties, when the field occupation numbers are quantum processes, quantum numbers, the vector field that it thus is so arises about them that defines the gradient of their motion and their acceleration and their equilibria. All right, I guess that's what there is today from reading of. That's section 3 there. And so the whole theory must be based solely on PDEs and their singularity-free solutions. All right. And the next section would be the theory of relativity, and it's talked about how that's the Laplacian. So I'm going to try and figure out how to think about the Laplacian and the principal component analysis, which is what I'm thinking about, is how to establish this free original analytical basis, FOAB, or something like that, that makes it so that I can provide Einstein's field theory classically first, and then with some sort of unified magnetic electric field for Maxwell and Lorentz, a system which makes for then this theory of some potentials is to be really a theory of potential fields, where an abstract potential field is what we're attaining to, and then it just so happens that the theory of harmonic functions is some kinds of potential fields, but it's really just an extension, and so that's something else we'll figure out, but that will all be defined in terms of the classical, the superclassical, that then will be figured out how that can be made in terms of models of matter as a metaphor to models available to sense that are immediately translatable to these models according to object sense and number sense and reason. And because you can't really, you can't make an infinite ruler, but you can imagine a line and this kind of thing. That's how it's going to work out. Then this axiomless natural induction results in axiomless natural geometry. It's Euclidean, then dot, dot, dot. The space goes back forever, time goes on forever, or vice versa. There's a ray of time, that there's 3 or 6 rays of space or dimensions of space, and that it so works out that then all these higher theories about the more and more and more from material points being surfaces to their constituent deconstructive account as of being particles, as of being on a smooth continuous manifold, that these are the sort of things that make it so then the fundamental physics has enough intuition and not too much more. I mean, you can't really expect somebody to stare at a wall for 8 years until they gain enlightenment, which would be a great thing, and it's a great thing if you can attain enlightenment of the enlightened mind, and also come back with a theory of physics. But the idea is to make it so that in a brief enough summary, you can present somebody enough of these ideals, basically with the same, first of all, the same classical paradoxes of logic, like Zeno's laws, that with a classical education, then it's just extended to arrive at the resolution of all these paradoxes, or lack thereof, if there are none. Well, great. I hope you enjoyed this today. I kind of do. I have a theory of everything. All right, goodbye.